Welcome to Lesson 11E, Gravimetric Settling of Particles in Ducts. We're going to discuss gravimetric settling of particles in horizontal ducts, and we'll talk about the difference again between laminar and well-mixed, just like we've done previously. First, I want to give some approximations and assumptions. We'll consider monodispersed spheres falling by gravity. We'll assume steady flow. Of course, for the well-mixed or turbulent cases, that means in the mean. Even for the laminar case, it's not actually steady because each particle is falling. That's an unsteady process. But in the long time average, it's steady. If the particle hits the bottom, it sticks there. Consider the laminar case first, where there's no mixing at all. This is an extreme case. The well-mixed will be the other extreme. We have some mass concentration coming in of these particles, and we also have some average speed. We're not going to worry about boundary layers and stuff like that. Just pretend this velocity is steady. Sometimes we'll use C naught instead of C in. This is a duct, like an air conditioning duct or a duct that's carrying pollutants from some process to a stack to go outside or to some air cleaner before it goes outside. The duct has height h. We're looking at the two-dimensional case, but you can apply this with a little bit of modification for round ducts as well. Well, this is very similar to particles settling in containers that we've already talked about. In fact, if I imagine looking at a little slice of this right here at the beginning, where we have this random distribution of particles, imagine that I'm moving with speed u with a little camera with a slot that looks like this, that I see just a portion of this, and I move with capital U to the right. So this would be at t equals 0 when I start. At some other time t equal t1, we're looking at this little slice. So what would I see? I would see that there's an interface of clean air and then a lower portion that has the same concentration as the beginning, C naught or C in. And you can imagine you keep doing this. At time t equal t3, that interface has fallen. The interface is moving at speed vt, by the way. We've had more particles build up on the bottom of the duct, but there's clean air on top and dirty air at the bottom. Finally, as we keep on moving downstream with the flow, we get to this final box here. I'll call this t equal t critical because at that point we have removed all the particles and all the air in there is clean. So from there on, the air is totally clean. Once we've reached that critical time when we're moving with the flow, we can also think of that as a critical distance, xc. In terms of the particle speed, we have a capital U and we have a vt, and the net particle velocity vector is the vector sum of those two. If you do a little trig, this interface is a straight line at an angle. I'll call it alpha. Alpha is the arctangent of VC over U. Well, I think you can already see that since this is so similar to what we've just talked about of settling in containers, we can do a simple Galilean transformation between x and time, namely x is capital UT, or t is x over u. So all the equations from the previous lesson settling in a container are still valid, except we replace t by x over u. It's this idea of the camera moving with the flow, and what we see at these locations is exactly what we see in the container settling case, except now this is unsteady in time, but we can translate to distance by this transformation. This is in fact the key to doing these problems then. I have this typed up here. To get our equations, we transform from settling in a box or a container to settling in a duct. So these are the equations we had before. Tc was the critical time. For the laminar case, we had C average over C naught as 1 minus T over Tc. We had our grade efficiency as T over Tc. And after some critical time, if the time is greater than critical time, I think I put my greater than or equal there instead of the less than or equal to here. It doesn't really matter. I'm just not being consistent. But anyway, after T is greater than Tc, we have no concentration because they've all settled. So all we have to do is apply our transformation that we just wrote. That is, everywhere there's a T, we set it to x over u, and Tc will be xc over u. So let's plug that in. Tc is xc over u, and that's h over vt. So we have an expression for the critical length, xc, is hu over vt. This is now the critical length where we used to have a critical time. Physically, this is the x location from the beginning of the duct to this location here, xc. This is the location where all the particles have now fallen to the bottom of the duct. And then from there on, it's clean air, as I've already said. As for grade efficiency, for this particular diameter, A to dp is T over Tc. We use these two equations. T is x over u, and Tc is xc over u. So this just becomes x over xc. So we have our equations for settling in a duct of height h. For the laminar case, with no mixing, we have a critical length, and then we have the same equation we had up here, except we're replacing T over TC by X over XC. And that's all there is to it. We have our answer. So think about a duct. This is a horizontal duct, by the way. If it's not horizontal, you have to do some other trig. Of course, if it's vertical, then you won't have anything settling. But for a horizontal duct with some U coming in from the left and a monodisperse uniform distribution of particles with settling speed Vt, you get an interface that just comes down like that, a nice straight line. Again, that angle is just made up of U and Vt. If this is also the x-axis along this bottom wall, this would be x equals 0. This would be the critical length xc. And we're talking about the height being h. So you can think of xc as the distance at which it takes a particle starting at the very top of the duct to get all the way to the bottom of the duct, falling at speed Vt. And these particles collect at the bottom. If this duct has a total length L, we draw that here, you can also call this LC. So I'll use both XC or LC depending on what we're talking about. Let's do an example problem. Dusty air enters a horizontal duct. I give the length 14.4 meters and the height 6.0 centimeters. Watch your units, that's centimeters. Average speed, very slow flow, 0.2 meters per second. And normally you'd have to calculate the settling speed, but I give it here in this problem just to make things go faster. But you know how to do that for any conditions already. Calculate the removal efficiency eta for these particles, and we'll assume laminar settling and all the other things that we've assumed already. So here's our solution. The critical length I'll calculate first, or XC, whichever one you want, is H times U over VT. Plug in the numbers, and I get 48.0 meters. That would be the length required for these particles at this flow speed and with this channel height to fall to the floor, and from then on, everything is clean. So eta is 100%, or 1, for x greater than xc. C average over C naught is 0 for that case. So if I had given you a length here, L, that was bigger than LC, you wouldn't have to do anything else. You'd say that eta is 100%. Well, here, L is less than LC here. So eta dP is X over XC or L over LC. Typically, L over LC makes more sense, so we'll use that most often. Plug in L and LC, and I get 0.30. So eta at this dP is 30%. This is the laminar case. Now remember, this grade efficiency is eta as a function of dP. If we repeat this analysis for different particle diameters, so we'd have different diameter, you'd get a different VT. You'd have to know the density and the temperature and pressure, of course, as well as the diameter to get VT, but you know how to do that. So let's imagine doing this for several different values of dP. Let's consider our duct. For this particular problem, we have a U, we have an H, and our duct length is such that it's shorter than the critical length. So for these particular particles, critical length is somewhere way out here. Call that dP1, which is the particles that we are looking at where we had 30% cleaning. It looks more like 50% on my sketch here, but imagine that that's 30%. I ran out of room on the right. So this is LC for dP1. If we had heavier particles, this would be LC at some other diameter dP2. The heavier particles would have an efficiency by the end of this duct of 100%, whereas eta of dP1 was 30%. And then obviously, if the particles are smaller or lighter, they would have an LC that's way off the page here. If all these particles are the same density, these would be smallest of the three, this would be the largest of the three, and this would be the middle diameter. So the math is pretty simple here. Now let's look at well-mixed. Again, some people call this turbulent gravimetric settling in a duct. Again, it's turbulent, meaning there's all these eddies moving things around. But well-mixed is more than just turbulent. Well-mixed means that you have such mixing that at any slice, let's just take a slice here, you have a uniform distribution of particles. It's just that now you have a high concentration at the beginning of the duct and a lower concentration further downstream in the duct. Theoretically, you never have pure, clean air because there may be still a couple particles left floating around like these guys here, even very far downstream. But we can use our same transformation, pretending we're a camera moving along. Here you'd see a uniform distribution. When you got to this point, you'd still see a uniform distribution, but it's not as concentrated as the first one. And then by the time you get down here, you have very few particles in there compared to the first two cases. We do the exact same transformation that we did with the laminar case. So now let's look at the equations for settling in a box or a room or a container of height h. We had the same critical time, remember. Both the two extremes, laminar and well-mixed, use the same critical time, so that's the same as we had. The difference is we have this exponential equation for mass concentration or the grade efficiency. The key is that we use the same transformation as we did in the laminar case, namely T equal X over U. TC is XC over U. And so XC, or LC if you want to call it LC instead, is HU over VT. Same as before. In other words, we replace T over TC with X over XC everywhere. And so the critical time becomes a critical length. And for well-mixed settling in a duct, we have this equation for eta and for C. This equation transforms directly into that equation since T over TC is the same as X over XC. And as I like to say, that's all there is to it. Let's compare the two cases, laminar and well-mixed. These are both extremes. I'm going to plot C as a function of X. I'm going to set this level to be C naught or C in. We use those terms kind of interchangeably, down to 0. And what happens is for the laminar case, we start at C in and we have a nice linear line to what we're calling XC, the critical length. So this is the laminar case. The well-mixed case starts at the same slope, but it is an exponential decay. So it looks something like that. Theoretically, it never reaches 0, but it asymptotes to 0 because it's an exponential equation. And then typically our actual case is somewhere in between these two extremes. The laminar case is the fastest that you're going to get these particles to settle. The well-mixed is the slowest that you're going to get them to settle. And then the actual is typically somewhere in between. So in other words, laminar settling is the best case scenario. Well-mixed settling is the worst case scenario. And as I illustrated up here, that curve I just drew, those two curves will actually shift to the right or left if we have different particle diameters. These are for one diameter. We can also plot eta of dP, the grade efficiency, as a function of dP. And this will be very similar to what we had for the settling in a box or a container. We typically do eta as a percent. So we go from 0 to 100. Here's 50. It turns out that laminar settling will look something like this. It won't be linear because VT is not linear with diameter. It'll go up to 100% and then be 100% from there on. So particles bigger than some critical diameter, all the particles are removed with 100% efficiency from there on. So the larger particles are removed 100% in this laminar case. The turbulent case has this kind of S-curve that asymptotes to 100, but never quite gets there, theoretically. And again, 50% is a magic number where we call that the cut diameter. So this would be dP cut for the laminar case. This would be dP cut for the well-mixed case. You have all the tools you need to plot these curves because I can give you any duct dimensions. I can give you any temperature and pressure. I can give you a range of particles. You can calculate VT for each of those particles in some range, calculate the grade efficiency, both laminar and well-mixed, and then plot them. And so that's the kind of thing you'll be doing for homework. Let me just do a quick example with this time well-mixed. Exact same example we had for the laminar case. I'm just doing the well-mixed now. So we have the same XC or LC as before. We're talking about the same particles, the same VT, everything's the same. So this before was 48.0 meters, same as the laminar case. But now eta at this dP1, if we want to call it that, this dP is 1 minus exp, negative x over xc, or in terms of the actual L's of these ducts, the lengths of the ducts. The only difference here is you can do this one at any x you want, but typically all we care about is the actual duct length. So we're going to use L's for the most part. And so we plug in our numbers and we get 25.9%. So this is the well-mixed value compared to 30% for the laminar value. That makes sense based on our plot here. We know that at any given diameter, let's take this one here. If you go up this vertical grade efficiency, the well-mixed one comes first and then the laminar one comes next. Again, the laminar one is the fastest removal or the shortest removal in the duct. The well-mixed is the one that takes longest. The real case would be somewhere in between these two most likely. Just one quick comment. We can define a duct Reynolds number. RE duct is rho U H over mu. And my comment is do not confuse this RE with the RE of the particle. These are two different Reynolds numbers. This one's a lot bigger, of course, because we're using a capital H instead of a DP, and we're using a U, which is typically much bigger than VT. This is the same Reynolds number we use for pipe flow and channel flow in our fluid mechanics course. These are at SATP conditions, so my density is given as 1.184 kilogram per meter cubed. The average velocity in the duct was 0.20 meters per second. My height was 6 centimeters, which is 0.06 meters. Watch your units. And then mu, that's the mu of SATP, and I get 768. Why do I calculate that? Well, you recall from your fluids class that for ducts and pipes, remember that number 2300. If the Reynolds number is greater than about 2300, it's considered turbulent. If it's less than that, it's usually laminar. So here it is laminar. So our 30% value is probably more close to real life than the well-mixed case is of 25.9. So that's how you figure out whether it even has a chance of being well-mixed, whether it remains laminar. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.